reproduce 24 times, leaving a single candidate out in each bin, such that the 4 bins which failed identified the essential genes, which when brought together in this reprogramming experiment were alone sufficient to drive pluripotency. And these now famous genes, ACA4, SOX2, PALM4, and MYC, have since been modified. You can do it with NANOG, you can do it with Win28, you can substitute LMYC for NMYC, you can substitute for SOX family members. There are cocktails now which can drive this reprogramming. Now, with refinements from Shinya's lab as well as that of Konrad Hochadlinger and Rudolf Janisch, we were able to produce bona fide pluripotent cells which satisfied the functional criteria of embryonic stem cells. That is, they could primerize the mouse embryo, generate contributions to all tissues, and be transferred through the germline. And then with this publication, which was in late 2006, it then became clear that we had to test whether these factors were sufficient to induce pluripotency in human cells. And indeed, it's a testimony to the robustness of this platform that just a little more than a year later, there were 3 groups that reproduced direct human somatic cell reprogramming, and then very quickly thereafter, this spread to, I would say, dozens of groups. So today, we have improved technologies and approaches to reprogramming, whereas most groups have used dermal fibroblasts for skin biopsy. A number of groups, our own included, has recently published that from a simple 10 cc venipuncture sample that can be drawn in any office, you can directly reprogram from the mononuclear cells of blood and generate a patient-specific iPS cell. So early on, we did this in a proof of concept to generate a repository of disease-specific lines, and just our initial production included the classical ADA immune deficiency, which is well-studied here and used in gene therapy, Gaucher's, models of muscular dystrophy, chromosomal abnormalities like Down, genetically more complex conditions like Parkinson's and diabetes, and this list is increasing at Harvard and internationally. At Harvard, we've established the Harvard Stem Cell Institute IPS Core Laboratory. My colleagues Doug Melton, Chad Cowan, Konrad Hochadlinger, Kevin Egan, and others are contributing to this core. There's been an enormous appetite in the scientific community for using these cells. It's been distributed to, I believe now, almost 200 different laboratories. So what I'd like to do is illustrate a couple of examples of how we're using these stem cells to have a fresh approach to time-honored questions. Here's the work of Kevin Egan and colleagues, where he's taken a patient with Lou Gehrig's disease, generated patient-specific iPS cells, and then demonstrated using techniques that have been pioneered by work from Tom Jessel and Hinek Victorly and others, the directed differentiation into both motor neurons and glia. And there's a tremendous biology that's grown up around the work of Cleveland and Maniatis and Goldstein and Egan and others that suggests that there's 2 processes at work here in ALS. There's both a homicidal tendency on the part of the motor neurons to not survive, but interestingly, there's also, a suicidal tendency. There's this homicidal tendency of the glia to liberate toxic factors which affect accelerated motor neuron death. And working with Lee Rubin, Kevin's group is now configuring drug screens that would antagonize this toxic factor, but also improve the survival of the motor neurons directly. And it's through these kinds of strategies that one would anticipate harnessing the value of these patient-specific iPS cells in the drug discovery program. We have collaborated with Sandra Leone's group. Sandra recently moved from Children's Hospital in Boston to Children's Hospital in Philadelphia. But we generated iPS cells from individuals with Down syndrome, and they carry the trisomy 21. Sandra's work has been asking a question about this fascinating observation in individuals with Down. that even though they have a childhood predisposition to certain leukemias, they tend to have a reduced lifetime incidence of solid tumors. And she's related this to restrictions on neoangiogenesis in individuals with Downs, and she's reproduced that in a mouse model that carries the Down syndrome critical region 1 gene. This is a protein that acts as a negative regulator of calcineurin-mediated angiogenic signaling. And what we did together with Sandra was to create tumors, teratomas, from normal individual iPS cells as well as those from individuals with Down syndrome, and then demonstrate by quantitative assessment of the microvascular density that the Down's tumors could not support the same degree of new vessel growth, providing perhaps substantiation of her observation that attempts to explain why there might be reduced solid tumor formation in Down's individuals. So these are just two examples where the iPS cells are giving us insight into these two different disease conditions. Now, what I want to talk about is a couple of stories where we've started to learn some very interesting fundamental principles of reprogramming. And the first is the relationship between telomerase and telomerase function, known to be critical for cellular immortalization, and the reprogramming process itself. What has been known is that the cocktail of 4 transcription factors activate an entire network of genes that are required for pluripotency, including the reactivation of the catalytic subunit of telomerase. Here are just 6 different examples where the fibroblast, which is absent expression of telomerase, has reactivated the expression in the reprogrammed state. You can also see this above by telomere length analysis that the rather shortened telomeres of the fibroblasts are regrown with reprogramming. Now this mimics what's been observed in somatic cell nuclear transfer, where one can actually reactivate the telomerase machinery through reprogramming and lead to the regrowth of telomeres. Now with iPS cells, what we've been able to do is literally subclone the fibroblast and demonstrate in 3 independent subclones that the telomeres will regrow. So the reprogramming is not simply identifying those rare cells in the population that have retained long telomeres and so therefore are more susceptible to reprogramming. The reprogramming process itself reactivates telomerase. So Sunit Agarwal in my group has been interested in asking, using a disease-specific model, whether or not the reactivation of telomerase is an essential feature of reprogramming. And for that, he turned to patients with a disease called dyskeratosis congenita, which has been linked to defects in the telomerase enzymatic machinery. And indeed, one can find mutations that influence the catalytic subunit of TERT, the RNA component TERT, or various RNA binding proteins like discarin, which act to bind and stabilize the core TERT. And there's some fascinating manifestations of this condition, but we are particularly interested as hematologists because we're seeing presentations in the pediatric hematology clinic of bone marrow failure. So Sunit obtained fibroblasts from individuals and then asked whether or not